All right, good morning. Let's talk about electrons configuration. So electron configurations you can think of as the arrangement or how they're set up, the arrangement of electrons, I'm going to abbreviate by saying E minus, in an atom. So in essence, how are electrons set up or around the nucleus of an atom? So we can write out the electron configuration of atoms using electron configuration notation and orbital diagrams. So we'll kind of talk about that. I'll show you some images. We'll go from there. So we're just going to do an example. The electron configuration for carbon is 1s2, 2s2, 2p2. So there's just a couple of things for us to take into consideration here. So the number in the front, this number right here, the 1, the 2, the 2, that number indicates the energy level. So the energy level, or how far you are away from the nucleus. So the energy level, also known as or called the quantum number. So that's two words. Quantum number. The letter indicates, so the S, the P, those letters indicate the sublevel. So indicate the sublevel, or also known as like kind of the shape or the type of orbital. So electrons are orbiting around the nucleus in certain shapes and or certain types. And so we have 4 different types or shapes. Those are going to be there's an S, there is a P, there is a D, and there's an F. And each of these different sublevels or shapes have different numbers of orbitals. So the S sublevel has 1 orbital, and each orbital can hold 2 electrons. So we're looking at the next one, each P sublevel can hold 3 orbitals and can hold 6 electrons. Each D sublevel can hold 5 orbitals, and so how many electrons? 10. And then each F sublevel has 7 orbitals and can hold 14 electrons. So you may have seen this before in the video on Friday. We kind of went through and showed the different orbitals in that video. So if I was looking at my periodic table, so I'm going to pull up my periodic table, and I'm looking at the periodic table. These are the different places where the different orbitals or sublevels are. So if you look at the periodic table, you can kind of see different sections have different types of electrons or subshells. Sorry about that. And so they have different subshells or sublevels of electrons. So anytime you're over here on this left side, that's going to be your S sublevel. Anytime you're in the middle, this is going to be the D sublevel, and this is going to be the P sublevel and the F. And so we'll get back to what that means more in a little bit with those different levels. So kind of continuing on, we have a superscript. So the number that's up top, the 2, then that number, the superscript, indicates the number of electrons in each level. So indicates the number of electrons in each sublevel or each orbital. And so kind of just going through this number right here, the 2, that adds up to be 6, which is the number of electrons for a neutral atom of carbon. So you can kind of just start working our way through. We can have these different examples. So we have oxygen has 8 electrons when it's neutral, so we'll say 1s2, 2s2, 2p. Remember, we said the p orbitals can hold up to 6 electrons. So we could put a 6 there, but we don't need to because that would be too many electrons for the oxygen. We're going to put a 4. So now you can note that the 2, and the 4, that's 8. That's 8 electrons that oxygen has. Great. So if we're going a little bit further, we can talk about silicon. And silicon is going to have 14 electrons, so 14 electrons. We're going to have 14 electrons for silicon, and kind of going in the same order: 1s2, 2s2, 2p6, 3s2, 3p2. And so that number 2 plus 2 plus 6 plus 2 plus 2, that's going to be 14. That's going to be the electron configuration, or how it's set up around the nucleus for the electrons for silicon. Calcium has a 20 electrons when it's neutral, so we're going to go with 20 electrons. You start off 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And so some things you may notice is that we don't have a 1p. We don't have other kinds of different levels that we'll talk about right now. So if we're looking at calcium, calcium is number 20 on the periodic table. So number 20 on the periodic table. Let me get rid of all this stuff. And blow my nose again. So we have calcium is right here on the periodic table. And so we said that this is the S, this level over here is the S block. This is the D, this is the P, and this is the F, which we won't get down to very much. So, and looking at this, I'm going to start with hydrogen. This is my 1s1. This helium should be over here theoretically, so that would be 1s2. Then you start working your way down. So I'm trying to get to calcium. So this is 1s1, 1s2. I work my way left to right. Then I come back down here. This is 2s1, 2s2. Then I'm working my left to right, top to bottom. This is 2p1, 2p2, 2p3. So you notice everything will build on top of each other as you're doing these electron configurations. Then you work your way down here. This is the 3s1. So if I said what was the electron configuration for sodium, I'd end at 3s1. 3s2, then I work my way to the right. That is 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, so on and so forth. Then we get down to this fourth level. This is 4s1, 4s2. And so in essence, you can kind of just keep building left to right, top to bottom, and you just put them all together. So your electron configurations are always going to be in the order 1s2, 2s2, 2p6, 3s2, 3p6. Then you get to 4s2, and then from 4s2 you go to this level, which is the Ds. And because of the amount of energy there, you have this number goes down one. So 3d10, and then back to 4p6, so kind of working your way left to right. Then you go down to the next level, 5s2, 4d10, 5p6, then you go to 6s2, and then actually after 6s2 you go to 4f14, and then 5d10, and so on and so forth. This is always the same progression of electron configurations. So you can kind of look at the number of electrons present in your atom, and you can stop when you've kind of reached that, the subscripts add up to be that value. So continuing on, if I'm looking at like fluorine, so fluorine has 9 electrons, 1s2, 2s2, 2p, we're trying to get this number to be 9, 5. That would be the electron configuration for fluorine. Iodine, the electron configuration has 53 electrons. So lot 1s2, 2p2. So if we're kind of just working our way down the periodic table, we can kind of find iodine. So iodine is down here, 53. So you start off 1s, 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10, 5, this is going back to 4p6, then you work on your fifth row, 5s2, this is back to 4d10, and then 5p5. So kind of in essence, you're just adding up those different values, and you'd end up at 5p5. So we wrote this a little bit wrong. So you have 5s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. So that would be electron configuration for iodine. Iron has only 26 electrons, so you'd start off 1s2, working your way down 2s2, 2p6, 3s2, 3p6, then 4s2, and then you actually end with Ds, because you get in that D subblock, and you'd say 3d10. I'm sorry, 3d6. And so all these values, 2, 2, 6, 2, 2, 6, 2, 6, that's going to add up to be 26 electrons. All right, so that's just kind of like the progression of the different levels of electrons. And so you may have looked at this, you're like, what is S, P, D, and F? That's basically the shell, the shape of the electrons and how they move around the nucleus. So I want to just show you guys this thing. This is kind of show you the shapes for S, P, D, and F. So your S sublevel or shape is just like a ball. So imagine your nucleus in the middle, and you have this ball around it of which the electrons are kind of orbiting around the nucleus. This gets a little crazier. Orbitals. So if you look, this is kind of showing it's almost like an hourglass in 3 different directions. So you have the px, the py, the pz, kind of showing you the different directions in which your electrons are going. And so in each of these orbitals, you can have 2 electrons, because there's 3 of those orbitals, each can hold 2. You'd have a total of 6 electrons for the p orbitals. Then the d orbitals get a little crazy, shape-wise. Orbitals. Whoa, whoa, getting crazy, D's. Orbitals. Whoa, orbitals. Oh, instrumental. Wow. So that's this general shape. I'm not going to ask you to draw those. I would know about the general shape of the p orbitals. And then back to the s. The d. Sorry, that was the p, and this is the d. Whoa. So if you want to use that as a soundtrack for your life, the orbitals, I can try to find that video for you guys. Anyway, so continuing on, those, like I said, those different letters are the different shapes of the electrons. And so here's just a couple more rules I want you guys to be aware of when you're filling in and kind of looking at how electrons go around the nucleus. So this first idea is Aufbau principle. And Aufbau sounds German because it is. The Aufbau principle basically states that electrons fill orbitals that have the lowest energy first. So in essence, if you have any electrons, you'd start off in the nucleus. This is kind of showing you as you get further and further away from the nucleus, the energy increases. So the very closest part to the nucleus, I'd have 1s2 orbital, which remember is like a ball. Then from there, you move out further away. So this would be like your 1s. Then you move away further out, that would be your 2s. So then you would move further, energy would be 2s. Then after that, it gets bigger and bigger, you get the 2p. And so then you'd have 2p6 you can fill up. Then after that, you'd have the 3s, then the 3p. So basically, as you get further and further away from the nucleus, the amount of energy required to keep that electron there increases. You get the 4s, then it goes back down at 310, and then 4p, and then 5s, and so on and so forth. It keeps going. So that's kind of like the progression of the amount of energy required to keep those electrons there. So electrons in the 3d orbital have a lot more energy than electrons in the 1s. Depends on how far away they are from the nucleus. All right. So continuing on, I have two more rules kind of determining how you put in electrons into the orbitals. This other one is Pauli exclusionary principle. So in essence, if two electrons occupy the same orbital, they must have opposite spins. So remember we said each orbital can hold 2 electrons, and then different sublevels have different numbers of electrons. But each orbital can hold 2 electrons. So in essence, if you have your 1s orbital, we can write it this way, where you have, like, this is the line that we're showing, the 1s is underneath it. If I have 2 electrons there, one is spinning that way up, and the other one is spinning down. I know you're kind of looking at it, you're like, why can you not make the full arrow? Well, because that's too much work. We're not going to do that. So in my 1s orbital, you have 2 electrons. In my 2s orbital, I have 2 electrons, so on and so forth. So one electron spinning one way, one spinning the other. Last rule for today is this idea of Hund's rule. So in essence, Hund's rule is when electrons that occupy orbitals of the same energy will have the maximum number of electrons with the same spin before pairing. So if I went to like the 2p orbitals, so 2p, remember, has 1, 2, 3 orbitals. You would have, let's say I had 3 electrons. 1 electron, 2 electrons, 3 electrons. So I know you're wondering, like, why are arrows representative of electrons? Because it's kind of representing the draw or the spin of electrons. And so that would be like 2p3. If I went to 2p4, 1, 2, 3 orbitals in the 2p, 1 electron, 2 electrons, 3 electrons. Remember, they all want to be by themselves first, and then eventually you'd have to pair up and then have that opposite spin. So electrons are spinning around the nucleus in certain ways, and they are going opposite from each other. So we will continue drawing more and more tomorrow, but hopefully this kind of guys get you started and didn't thoroughly confuse you too much. We'll continue on with more about electron configurations tomorrow. All right, have a good